welcome back to Applied Materials and Corrosion. This time we're going to talk about food and medicine, because obviously materials that are used in the food industry and materials that are used in medicine have similar requirements. So the main requirement is that they stand up to sterilization of some kind without turning into mush or releasing any toxic compounds. They're not allowed to be toxic on contact, and they shouldn't be soluble in water. So how are we going to sterilize our material? We can do it in a variety of ways. We could use the normal method, which is steam. Typically superheated steam, so it would be maybe 150 degrees, 150 to 180 degrees, typically hot steam. Or we could use some other technique, and the other technique that we would use would be in the household, would be bleach of some kind. So we would use some kind of oxidant. That would be O3, for example, ozone, or chlorine, CO2, chlorine bleach, peroxide, which is similar to O3, which is why I wrote it. So either ozone directly, or chlorine as a bleach, or peroxide as a solution. We could use any of those. We could also use energy directly, so we could use light, UV, or plasma. That gives out all of our materials a starting problem. So if we take any polymer that can hydrolyze, polyester for example, it's going to have trouble in steam. If we take cellulose, steam is going to degrade it fairly quickly, not super quickly. We can treat cellulose with steam, but it will degrade. If we use an oxidant, there are lots of chemical processes that can occur, and so obviously polymers are going to be a problem. So that will push us out of there. Also metals that can be oxidized easily, we're going to treat them very badly. So iron, for example, even copper are difficult. They're not impossible, but they're difficult because we're going to treat them badly. Ultraviolet or plasma, particularly good for destroying polymers, which is good for sterilization. It's bad if we need a polymer for our application. So that reduces our possibilities. Depending on which application we have, we will have some subset of sterilization techniques that are used, and we may have a choice. So if we are doing brewing, for example, we will typically stay over on this side because we have a closed container and we might need dark places, or we might have a tap and it's difficult to get ultraviolet light in. It's difficult to get plasma inside a closed container that is very large, because we need low vacuum for that, or medium size vacuum for that. We can do it in the air, but the size of the plasma is comparatively small, and then we'd have to move it over the whole sample, so it's impractical to do a large still with a UV or plasma. If we want to fill it up with bleach though, we could do that, and let's put persulfate as well. So that is SO, can't remember, SO5, S2O4. Persulfate is also a chemical oxidant. So we could also apply steam. That's quite common and it's cheap, and it's often used in the food industry because that is the sort of old tech standard. But steam is also very brutal. When we heat water up enough, it becomes quite oxidizing. As we heat water up, the properties change and it becomes more and more oxidizing, and that makes our metals, for example, less and less able to sustain it. So steam is quite brutal. if we look at what we would like on the surface of our material to make it less attractive to bacteria, the simplest way to do that is to make it as smooth as possible, because that reduces the amount of crevices where things can hide. And our engineering design part is to not have any hidden holes. That avoids another problem or another advantage that we can have if we have structures of a very small size. We can make it difficult for different bacteria to adhere, but usually, because we're going to apply different forces to our material, usually the simplest and cheapest way is to try to make it as smooth as possible, which does reduce the number of materials that we can use. Something porous is very bad. So if we think of metals that we can use, stainless steel is something that springs to mind immediately, but there are of course various grades of stainless steel, and only the better ones are really suitable. Lower qualities of stainless steel have a tendency to corrode, and that's worse than having iron, because then you release chromium ions or nickel ions or vanadium into the food or the medicine. So typically we stay at relatively good types of stainless steel, so relatively corrosion resistant types of stainless steel, but also titanium, which is quite resistant. However, on the other hand, some materials used in the past, like tin for tin cans, or some materials used still, avoid this problem a little bit. So those are then heat treated in the absence of oxygen, steam treated in the absence of oxygen. They don't oxidize too badly, and then they are anaerobic for the rest of their lifetime. A tin can or a can is a big problem to users if they don't know how to use them, because if you open it and leave the material in there, the metal starts to dissolve into the food quite quickly as soon as it is exposed to oxygen, because then we can have a corrosion cell. Aluminium is quite difficult because we have to treat it to have a layer on the surface which is not going to release any material, which is not going to be susceptible particularly to steam. Steam is quite aggressive to aluminium, but once aluminium has a strong oxide layer on it, it's fine. It depends how long you want to use it, how many cycles. So typically aluminium isn't used very much in machinery because it has to be sterilized many times, but for single use it's completely fine. For medicine it's not used so much because aluminium ions in the body have some relatively strong interactions, so they don't use it very much. Tend to stay with magnesium and other metals. If we want to use magnesium in an implant, for example, then we cannot sterilize it with steam or with oxidants. We have to use a different technique because the magnesium is going to oxidize completely. If we use copper or silver, the copper and silver ions that dissolve off it have a self-sterilizing effect, and again we would prefer not to use it in combination with steam or oxidants, because we will tend to get a dissolution of the metal and lots of things locally near the site, which obviously if we're about to put it in contact with food or a body, that will be really bad. But copper is quite soluble, so we have to be a bit careful. So it's not very good in acidic conditions. Copper acetate is quite soluble. Also nitinol, which you would think is not very suitable because it's a nickel tin alloy, a nickel titanium alloy, sorry. It is however stable enough that it can be implanted into the body, and the titanium oxide on the surface of it reduces the amount of corrosion enough that it is reasonably safe. It is also quite easy to sterilize because of the titanium oxide layer on the surface. Titanium is a good example. Right, stop. So if we want to use a ceramic, we have a lot more advantages. We can heat them up to a higher temperature and nothing happens because they're not oxidizable, and most of them aren't. And many of the ones of choice would be glass, which is used both in medicine and in food. Aluminium oxides, zirconium oxides are quite well used in both. If we want a material that is hard and resistant to sterilization and reasonably good in contact with food or in contact with medicine or with the body or something. There is a problem, porosity is a problem, so if we make a ceramic, we typically have a problem there. That is the advantage of glass, because it's not a porous sintered ceramic. Typically it's made by fully melting it, and then you have no pores. Aluminium oxide is harder to melt fully, and so we tend to have a porous ceramic, but that can be very, very small degree of porosity, and it's just the grain boundaries are not the same crystal structure, so it's not completely melted and then fused. It's just annealed. So the advantage of ceramics is that they're hard. The disadvantage is, of course, that they can't be used as a seal, for example. There is, I'm going to stop, hang on. The other advantage that we might want, or the other thing that we might want to do, is grind some food or grind some material for use in medicine. And there we have a problem with loss of particles and self lubrication. So we would like our grinding head to not lose too much material that can cause problems. And that's good if we use it as ceramic, particularly an aluminium oxide ceramic, because aluminium oxide particles are not going to do very much if they get lost, as long as they're not too sharp. If we have glass particles, they're usually relatively harmless. As long as they're either very small, then they'll dissolve, or they're big, then they just fall out to the bottom. So those are better than if we take a hardened steel type. Then we are releasing particles that contain heavy metals into the food or the body, and that's often a concern. It's usually not very much, and they're usually not very soluble, but it is a concern, and ceramics are better for that, because we can choose one where the products are not very harmful. And we still get very high stability, and we get very high hardness. So if we take polymers, then we have a limited spectrum. If we're going to heat them up, they have to have a high melting point, or high glass transition. That would be things like nylon. But if we want them to be oxidation resistant, we will need a fluorinated polymer. So if we want something that's soft, something that we need to melt, we will need a fluorinated polymer, because fluorinated polymers are already fully oxidized. So like a ceramic, it is very, very difficult to oxidize them further, so we can bleach PTFE and nothing happens, because what's it going to do? Take on chlorine, swap the chlorine for fluorine. It's not going to do that. The fluorine has a better grip. So then we can do a lot of things. We can even expose fluorinated hydrocarbons to plasma, although it will then release really, really bad things. If we use normal conventional polymers with a high enough melting point, then we can heat them up, but we will have to be careful. We may have to treat them specially. We do have to be aware of hydrolysis reactions that can happen. So nylon has a tendency to hydrolyze, but not a very high tendency. Some types of nylon are reasonably resistant if they've got enough hydrophobic groups on them. If we have a polyester, it becomes more and more difficult, and they tend to be used very little. If we need a seal, we need it to be soft, and very often it's a fluorinated rubber that is used for the seal. So there's a special type, or there are special types of O-rings, special types of sealing materials that are fluorinated. And in both cases we can consider some common issues, which would be chemicals leaching out of the polymers and going into the food or the body or the medicine, and that would obviously be bad depending on how toxic they are. So there are strict controls onto what things can leach out. We can consider that in the case of silicones. So normal silicones have a reaction in which the silane cross-links with water. So it cross-links by reacting with water to form a hard polymer. Starts off as a liquid. It's not a melting process, so they're not cast by melting, they're cast by a reaction. And in that case, I'm just looking at my face looking weird here, in that case there is an extra sort called platinum silicone which is safe for food and medical use. The difference being that instead of having a tin catalyst, which is an organo-tin catalyst, it's only a tiny amount, but it is quite toxic, so it's not allowed in food, it's not allowed in medicine, it's not allowed in contact with animals. But there's another type which is catalyzed by a platinum salt, and that is considered to be safe. What can also happen is parts of the monomer or parts of the molecule can fall off during degradation or because they haven't fully cross-linked. So if we consider a polymer that's generated in the ways that you have carried out, only a few of the possible methods of making polymers make a tight chain length. Usually there's a bit of randomness involved, so you can end up with very short oligomers, and they can escape, particularly with silicone. So silicone typically contains small silicone oligomers which can reach the surface. This is particularly common in epoxy adhesives, where the reaction generates a stiff, hard matrix, which means that it's very hard for the small monomers to then get to each other to form polymer. And so typically there's a little bit of short chain material left, and that migrates to the interfaces. So it migrates to the interface to the other side, but it also migrates to the outside interface, and that can leach into the water, which is why epoxies are seldom, there are some, but they are seldom considered to be food safe. There are some that are food safe, but not very many. The same applies to other things. So if we take ceramics and particles are rubbed off them, we can consider them the same as leaching materials. Or if we take a ceramic that is a combination of different materials, the problems arise when something dissolves into the solution. So it's a fairly common problem that we have to watch out for. In the case of foods and medicine, there are regulations that prevent us from using materials that aren't tested, that we haven't shown don't leach things, and that can make it life difficult to start with, although a lot of things are allowed that you wouldn't expect. So there is not too much difficulty finding materials. Very often, however, if you make a device that contains many materials together, it becomes difficult to sterilize it because each one has its own requirements. So many polymers don't like hot steam. Many organic materials don't like oxidizing agents. Metals are not so good in combination with salt and oxidizing agents and water and light. So the UV is pretty good, is excellent on inorganic materials, but it tends to affect organic materials because that's its whole job. So the problem is biomaterials, biology is made out of biological polymers. So it is difficult to affect them and not our material itself. Okay, so this subject is really a little bit of an aside, but it is important to think about for other purposes, for the industrial part of this course, for all of the other teachers on the industrial side, that many questions are, what materials can we use in this application? And in the case of food and medicine, the major concern is surprisingly sterilization, and not will it hold my material for the time that it needs to. Sterilization is usually the problem. However, we do have one more aspect, which is packaging. For packaging, we have an extra requirement. Typically, packaging has to be light, or at least as light as possible, and fulfill its requirements. So you're supposed to be absorbing some kind of energy that's coming from the outside to prevent it from damaging the material or the food. Oops, I have to go phone. So the packaging typically will have to go through similar conditions, but it may also have to be light, although external packaging then will not be autoclaved or sterilized in some way. The internal packaging may have to go through the autoclave because it makes it possible to then keep the seal. So all of those materials also have relatively high requirements. They have to have a melting point above 150 degrees, maybe 180, depending on the temperature of the autoclave. And they need to stay sealed under those conditions. So they need to swell a little bit or hold the pressure. Then they need to contain the whatever it is, the medical or food device, without letting something in, so they need to have correct barrier properties as well. Okay, so we're going to go back off this topic and see what we've got left in our course so that we can finish off our material. See you next time.